Hello students, welcome to this new video presentation on gravitation part 1 which is prescribed in chapter number 8 of class 11 physics. First I will introduce the topic gravitation followed by Kepler's law, universal law of gravitation and then the gravitational constant. We are aware of the tendency of all material objects which get attracted towards the earth. That is, anything thrown up falls down towards the earth. Going uphill task is lot more difficult, tiring than going downhill. Raindrops from clouds fall down towards the earth. And there are many other such things which happen. Historically, it was the Italian physicist Galileo who lived from 1564 to 1642 recognized the fact that all bodies, irrespective of the masses, are accelerated towards the earth with a constant acceleration. He conducted a number of experiments and found the value of acceleration due to gravity, which is close to more accurate value obtained later. Further, in this field, a Polish monk, Nicholas Copernicus, who lived from 1473 to 1543, proposed a definitive model in which the planets moved in circles around a fixed central sun. Another scientist, Tycho Brahe, who lived from 1546 to 1601, spent his entire lifetime recording observations of the planets with the naked eye. Please note, naked eye. He compiled the data, which was analyzed later by his assistant Kepler, who lived from 1571 to 1640. Kepler could extract from the data three elegant laws that now go by the name Kepler's laws. Newton used these laws to propose a universal law of gravitation. All this we will study in this part of our video. I welcome you once again. Please note down all the important points as the same will help you in understanding the theories behind the subject. Kepler's laws. There are three laws and we will study the first law. The law of orbit. The first law is law of orbit. Every planet moves around the sun in an elliptical orbit with sun at one of the foci of the ellipse. Please see the figure here. AB is the major axis of the ellipse shown in brown color here, and ED is the minor axis. The planet Sun lies on the foci AB, and the distances, the nearest end is A and the farthest end is B. The closest point A is called perihelion and the farthest point B is aphelion. Perihelion occurs somewhere in January when Earth is nearest to the sun, and in July Earth is farthest from the sun, as shown in the figure. A is the radius of semi-major axis. AB is major axis and A is as shown in the figure. And R1 and R2 are distances of sun from A and B as shown in the figure. Second law. The second law states is called law of area. The line joining the sun to the planet sweeps out equal areas in equal interval of time. That means sun sweeps equal areas in equal interval of time. According to this law, planet will move slowly when it is farthest from the sun and more rapidly when it is nearest to the sun. Please see the figure 2 here, below here. Here sun is shown here and the areas delta A is also shown. The planet P is lying in the elliptical path as explained earlier. R, delta A, and positions of planet P and P dash are also marked in this figure. You please note down this figure. Then the area swept out by the planet of mass m in time delta t is delta A is equal to half into r vector half cross r cross v delta t, where delta A is the area and r is the radius and v is the velocity, and the area covered is the duration of the coverage of this area delta A is delta t. Rearranging, we get delta A by delta t is equal to half of r cross v into m divided by m, that is multiplying and divided by m. We get, so we get, and simplifying, that is equal to r cross p divided by 2m, because v into m is p, where p is the momentum. So here vector v is the velocity and L is, if L is the angular momentum, r cross p can be written as angular momentum, which we have studied in our earlier chapter. Therefore, for central force which is directed along R, L is constant. Therefore, aerial velocity V is equal to del A by del T equals L momentum divided by 2m. This is the same as the previous equation. Now we will take up law of periods, the third Kepler's law. The square of the period of revolution t of any planet around Sun is directly proportional to the cube of semi-major axis of the orbit. That is, t square is equal to a cube. You see the figure 1, figure A is the radius of the semi-major axis A. So t square is proportional to a cube, or it can be written as t square is proportional to r1 plus r2 divided by 2 whole cube. That is, a is equal to r1 plus r2 by 2. Therefore, VA is the semi-major axis and R1 is the shortest distance of the planet from Sun, and R2 is the largest distance from the distance of planet from the Sun. This is shown here. This is the largest distance is R2 and R1. This is as explained in this figure. Kepler's laws are valid for satellite also. We have taken the example of Earth. This can also be applied to other satellites also. Confirmation of Kepler's law of periods. Let us examine the data measured from the planetary motions, which is given in table A below. The column 1 lists the name of the planets, and second column gives the value of A, that is semi-major axis, in units of 10 to the power of 10 meters. The third column lists the time period of revolutions of the respective planets in terms of years. The last column, that is fourth column, gives a quotient Q is equal to T square by A cube. That is the formula of Kepler's law of periods, which is given in units of 10 to the power of minus 34 year square per meter cube. Please examine this data and it confirms the satisfactory application of Kepler's law of period. Now we will take a question to examine and understand the application of second law, that is law of areas. Question number 1. Let the speed of planet at perihelion P in the given figure below be Vp and the Sun planet distance SP be Rp. Relate Rp, Vp Vp to the corresponding quantities at the aphelion Ra, Va. Will the planet take equal time to traverse BSC and CBB? Examine this figure below. Here, the blue colored path is an elliptical path of the planet and S is located near point P. PA is the major axis of the ellipse. So, there are semi-major axis and BC is the minor axis. Yes, Sun is located here at this point. So, the distance PA is equal to 2A, where A is the semi-major axis and BC is equal to 2B, where B is the distance of small axis, minor axis. So we have to relate RP, that is the distance RP and velocity at P to the corresponding VA and RA at this point, A point. Therefore, the magnitude of angular momentum at P is given by MP, that is mass RP into VP. Similarly, R and VP are mutually perpendicular. That is, the distance and velocity are mutually perpendicular. Therefore, similarly, LA, that is angular momentum at the point A here, equals mass MA into RA into VA. Therefore, from angular momentum conservation, angular RP VP is equal to MA RA VA. Therefore, rearranging, Vp by Va is equal to Ra by Rp, because mass Ma is equal to Mp. Since Ra here, distance between Sun and A is greater than Rp, Vp will be greater than, Va will be greater than Vp from this ratio. Therefore, the area SBAC, this area bounded by the ellipse and the radius vectors SB, radius vector SB and SC is larger than SB PC, this area, that is the right hand side area of the dotted line is greater than the left hand side area, as you can see from the figure. From Kepler's second law, equal areas are swept in equal times. Hence, the planet will take a longer time to traverse BAC than CPB. This is the answer. Universal law of gravitation. Newton's law of gravitation states that everybody in this universe attracts every other body with a force, and this force is directly proportional to the product of their masses, and this force is inversely proportional to the square of distance between their centers. The direction of this force is along the line joining the particles. Thus, the magnitude of this gravitational force F, that two particles of masses m1 and m2 separated by a distance r exert on each other, is given by the relationship vector F is directly proportional to m1 and m2, and F is inversely proportional to the square of distance between the two particles. So, if m1 is the mass of body 1 and m2 is the mass of body 2 and the distance between m1 and m2 is r, then the universal law of gravitation states that the force between m1 and m2 is directly proportional to m1, m2 and inversely proportional to r square. This can be written as removing the proportionality constant. We can write the above equation as F is equal to G into m1 m2 divided by r square. Here G is called the gravitational constant and G is also known as universal gravitational constant. The value of G is 6.67 into 10 to the power of minus 11 Newton meter square per kg square in SI units, and its value is 6.67 into 10 to the power of minus 4 dynes centimeter square per gram square in CGS system. The dimensional formula of gravitational constant is m to the power of minus 1 L cube and t to the power of minus 2. The value of G does not depend on the nature and size of the bodies, and it also does not depend on the nature of the medium separating the two bodies, that is medium between the two bodies. Note, the gravitational force between extended objects like Earth and a point mass, the equation 1 is not directly applicable. That is, between Earth and a point mass, F is not equal to G into m1 m2 divided by r square. Each point mass in the extended body will exert a force on the given point mass, and these forces will not all be in the same direction. So here the direction of force will be different. Hence, we have to add up these forces vectorially. Please underline, we have to add such forces between extended objects and point mass vectorially for all point masses in the extended object to get the total force. Characteristics of gravitational force. We have studied about the basic definition and some important points about gravitational force. Now we will study about the characteristics of gravitational force. Gravitational force is always attractive and is directed along the line joining the particles. Both the particles experience forces of equal magnitude, that is m1 and m2 in the previous slide. They experience force of equal and opposite magnitude, forces of equal magnitude, and the direction is opposite. If F1 and F2 are the forces exerted on particle 1 and particle 2 respectively, then F1 is equal to F2. Since F1 and F2 are exerted on different bodies, they are also known as action-reaction pairs. The gravitational force holds good for long distances like interplanetary distances, also for short distances like interatomic distances. So the gravitational force holds good is applicable for large distances between planets as well as very short distances within the atom. Gravitational force is a conservative force. Therefore, the work done by gravitational force on the particle is independent of the path path described by the particle. So because it is a conservative, it does not depend on the path of the particle. Gravitational force depends on the initial and final positions only. Therefore, no work is done by gravity if particle moves in a closed path. Please see the figure here. Draw the figure as shown here. O is the origin, OX, OY and OZ are three coordinates which are mutually perpendicular to one another. A mass M1 is located at a distance R1 as shown in the figure. Similarly, another mass M2 is located at a distance of R2 from the origin. So, OM1 and OM2 equals R1 vector R1 and vector R2 called position vectors as shown in the figure. Therefore, the resultant of these two forces vectorially adding becomes R is equal to R2 minus R1 because R2 and R are in the same direction whereas R1 is in the different direction, hence R1 is minus. In vectorial form of force, F is written as F is equal to G into M1 M2 divided by R square into minus R. That is equal to F equals minus of G into M1 M2 divided by R square into R hat. R hat is the unit vector. Here the R hat is unit vector. That can also be written as summing vectorially equals F is equal to G M1 M2 divided by modulus of R cube into unit vector R. This is already discussed in a vectorial summation form. If we have a collection of points of masses M1, M2, M3 and N4, then the force on any one of them is the vector sum of gravitational forces exerted by the other point masses. Therefore, it can be written as F1 is equal to G into M1 M2 divided by R21 square into R21. Here is a unit vector. R21 is a unit vector plus G into M1 M3 divided by R31 square to R31 in the direction plus G into M1 M4 divided by R41 square into R41. Now let us solve a question on the gravitational forces. Three equal masses, question number 2. The three equal masses of mkg each are fixed at the vertices of an equilateral triangle ABC as shown in the figure. So here triangle ABC is shown. Part A. What is the force acting on a mass of 2m placed at the centroid G of the triangle? What is the force if the mass at the vertex A is doubled? Take AG, BG equals CG equals 1 meter. Please read the question once again and draw the figure. Here, first draw the triangle ABC. Mark points M, that is mass M at each vertex, that is at A, B and C. G is the centroid of the triangle. You can join it in such a way that all are meet at the point G. That is, if you draw a perpendicular from point B to AC at the center and then join it, you will get the angle between GC and GX coordinate X is 30 degrees. We know that the force F is given by the formula F is equal to G into M1 M2 divided by R square. Using this formula, we will calculate the individual forces in vectorial notation. Therefore, FGA is a force here acting upwards is equal to G into M is the mass here at A into 2M. 2M is the mass at the point G divided by R square. R is 1. So, therefore, it is Gm into 2M divided by 1 square into J. J is the vertical direction, unit vector in the direction of y-axis. Let it be equation 1. Now, FGB, that is the force between G and B, is given by Gm into 2M divided by 1, and its direction is minus I into cos 30 minus J sin 30, because we have to resolve this force in y-axis, x-axis as well as y-axis. Therefore, the y component is J sin 30 and x component is I cos 30. Therefore, let it be equation 2. FGC, that is the force here, is given by Gm into 2M divided by 1, and the unit vector in this direction is the component along x and y axis is I into cos 30, that is vertically up, I into cos 30 minus J into sin 30, because J here for GC, J acts downwards, and X in the X direction it is positive. So, I cos 30. Therefore, we have to add FGA plus FGB and FGC to get the resultant force FR. Therefore, Fr is equal to Fga plus Fgb plus Fgc. That is equal to, adding 1, 2 and 3, we get Fr is equal to 0. If you add here, cos minus cos 30 and cos sin 30 get cancelled, and this also, the J also gets cancelled. So, we get Fr is equal to 0. Now, part B. When the mass at the vertex is doubled, that is at A is doubled. When A is doubled, FGA, F dash GA becomes FG into 2M into 2M. Here M becomes 2M. Therefore, FGA will be equal to 4 into G M square into J. Let it be equation 3. And F dash GB is equal to FGB. Therefore, F dash GC will be equal to FGC. The resultant, if we add F dash GA plus F dash GB plus F dash CE, is the new FR. Therefore, adding 1 and 2, we get F dash R is equal to 2G into M square into J. That is the answer. Now, we will note some special cases, points about the special cases. The force of attraction between a hollow spherical shell and of uniform density and a point mass situated outside is just as if the entire mass of the shell is concentrated at the center of the shell. Point number 2. The force of attraction due to any hollow spherical shell of uniform density and a point mass situated inside is 0. Hence, the force of attraction due to a hollow spherical shell is 0. The gravitational constant, section 8.4. The gravitational constant was determined by Henry Cavendish. Hence, this experiment is also called Henry Cavendish experiment. The setup of Henry Cavendish experiment is shown on the right hand side. Please see here the bar. It has got the experimental setup, has got a simplified experiment setup, has got a bar AB has two small lead spheres, that is A and B are smaller spheres attached to its ends. The bar is suspended from a rigid support by a fine wire. This is a vertical thing, black line is a vertical wire and it is supported rigidly. Two large lead spheres S1, this is S1 and S2 are brought close to the smaller ones but on the opposite side. See, S1 is on this side and S2 is on the other side. As shown, the big spheres attract the nearby small ones by equal and opposite forces. So this is the force of attraction and this one is shown here by the arrows separated by a distance d. Therefore, there is no net force on the bar but only a torque which clearly equal to F times the length of bar. That is F, if capital L is the length of the bar AB, then the torque is equal to F into L, where F is the force of attraction between the big bar and the small bar. Due to this torque, the suspended wire gets twisted till such a time that restoring torque of the wire equals the gravitational torque. Please note, restoration torque equals the gravitational torque. If theta is the angle of twist of the suspended wire, the torque, restoring torque is proportional to theta. That is, the restoring torque equals tau theta, where tau is the restoring couple per unit length of angle of twist. Tau can be measured independently, example by applying known torque and measuring the angle of twist. So if we apply a known torque, we will get a standard twist and which can be measured. The gravitational force between spherical balls is same as if their masses are concentrated at their center. Thus, if D is the separation between the centers of the big and neighboring small ball, capital M and small m their masses, the gravitational force between the big sphere and its neighboring small sphere is given by the relationship F is equal to capital G into capital M into small m divided by d square. All these symbols are already explained as earlier. F is a force, G is a gravitational constant, capital M is the mass of bigger sphere and M is the small sphere. And D is the separation distance as shown in the figure. If capital L is the length of the bar AB, that is length of AB equals capital L, then the torque arising out of F is multiplied by L, capital L. Therefore, at equilibrium, this is equal to the restoring torque. Therefore, G into capital M, small m divided by d square into L equals tau theta. Observation of theta thus enables one to calculate G from this equation. Since Cavendish experiment, the measurement of G has been refined and currently accepted value of G is 6.67 into 10 to the power of minus 11 Newton meter square per kg square. With this, we conclude the part 1 of gravitation. In the next lecture, we will take up acceleration due to gravity, acceleration due to gravity below and above the surface of Earth, as well as gravitational potential energy. Please pause and study this video again and again and practice all the figures. Till then, goodbye.